In this video, we are going to look at section 14.7, problem number 22. Right? It's asking us to compute a triple integral of the function x squared over the region R, where R, they say, is the region inside of the sphere, but it's in the first octant. So they give you a sphere x squared plus y squared plus z squared equal to 1, but they say it's the part inside of the sphere, and it's in the first quadrant. So it's this sphere here, in the xyz plane. And they'll probably put less than or equal to on it just so that you know that it's in the solid region. This is a solid. Okay. What do we need to do? We need to, because the region is some sort of spherical region, we definitely would like to get away from Cartesian coordinates. If you set this up in Cartesian coordinates, it's not too difficult to set up. Could be a very difficult integral to compute. So let's set this up. If you did x squared and you did the typically dz dx dy dx, z would go from the square root, it would go from 0, this bottom plane here, okay, so we're in the first octant, up to the sphere itself. The sphere itself, when you solve for z, is the square root of 1 minus x squared minus y squared. Okay. And then, because you were looking at the z equals 0 plane, you'd have to do a dy dx problem to figure out what sort of region you were looking at in the xy plane, so that you know how to set up the other two regions here, the limits on the dy dx integral. You would then have to, when you set z equal to 0, you would get x squared plus y squared is equal to 1. And that would give you the top half of you would need the top half of a sphere, right? But it would only be this part of the sphere because we are in the first octant. So you would have to then go from y is equal to 0 up to y is equal to the square root of 1 minus up to the square root of 1 minus x squared. And then you would go from x is equal to 0 to x is equal to 1. What that would do is it would let you find the mass of this spherical wedge. Okay, I've plotted both the surfaces and the 3D region. And here is your density function. And this problem, we are going to call this our function sigma, x, y, z, a density function. This is x squared. So as in the cylinder problem, I've taken a couple slices of this thing. I think I've taken the x is equal to 0 slice, and you would get this shape here. And because x is a constant and it has no y's and z's, when you take x is equal to 0, you have this density function here that doesn't change in the yz plane. When you take another slice of it, I think I took a slice at 0.5 here, cut through this surface at half, you get another one of these little semicircular wedges. And the density function of those is constant because we took x is equal to 0.5, and that would be a density everywhere of 1/4 in this slice. Okay, so that's the problem we're being asked to compute, and if you confine yourself to Cartesian coordinates, this is what you've got to do. This could be very difficult, a hard integral. I don't even like the idea of thinking about how to evaluate it because of all these square roots. I think we're going to have a lot of trouble with that integral. Okay. So the idea is to switch into spherical coordinates because you're integrating over a spherical region. Why don't we move into spherical coordinates? Try in spherical coordinates. Okay. As in the last problem, you need to do this in stages. You need to take your density function and convert this to spherical coordinates. Okay, and remember that spherical coordinates is given by x is equal to rho cosine theta sine phi, y is equal to rho sine theta sine of phi, and z is equal to rho cosine of phi. Okay. So that's simply what I've done in this problem. I've taken the region that we were given. We were given this kind of wedge of a circle, and I've parametrized it. I've parametrized it as a function of, and since r is constant, this is a sphere of radius 1, so the only variables here are theta and phi, right? So this function should be 1 cosine theta sine, oh, sorry, my pen's not functioning very well, cosine theta sine phi, sine theta sine phi, and then the last entry would be cosine of phi. And that's what I've done here in this part of the code. Again, I've tried to plot the different regions. I've plotted the surface of the sphere parametrically rather than in Cartesian coordinates, square root of 1 minus x squared minus y squared, and tried that as a plot, parametric plot 3D. We plotted the plane. I plotted the 3D region. Here it is. I did the different density plots, right, to figure out what each of these densities and these different slices look like. And then I put all the plots together. So you should probably pause this video and try to recreate this code to get the below plots. All right. So we're trying to convert the difficult triple integral in Cartesian coordinates over to spherical coordinates, and we have our function sigma of rho cosine theta sine phi, rho sine theta sine phi, and rho cosine phi. Plug those in for this function and you simply get rho squared cosine squared theta sine squared phi. So here's our new density function. Okay. We then need to transform our region. Okay. Our region was going from z is equal to 0 up to this surface. Okay. So our z variable would go from z is equal to 0 up to z is equal to the square root of 1 minus x squared minus y squared, right? So picking up, we just need to compute our triple integral of our function rho squared cosine squared theta sine squared phi. And then we were trying to compute this as a d rho d theta d phi integral. These are our new variables, okay? But we have a compensation term. We have a compensation term, which is the Jacobian of the spherical coordinates transformation. So if you take your transformation to be a function of rho, theta, and phi, that's rho The more times you write this function, the more you'll get it. Cosine theta sine phi, rho sine theta sine phi, and then rho cosine phi. If you were to take the Jacobian of that transformation and then take its determinant of that Jacobian, t, you will get rho squared sine of phi. So this is what will go here, rho squared sine of phi. Okay. And then the limits for this region are pretty straightforward. The limits for this region are describing this spherical region is that rho, the radius goes from 0 to 1. Okay, this is a solid region. If we're looking at this as spheres moving out, the radius of those spheres is going from 0 to 1 to account for this solid. And then theta will go from 0 to pi over 2. And phi will go from 0 also to pi over 2. Okay. And there is the new integral you have to evaluate. Okay. It's absent of a bunch of square roots. It is probably going to have to remember some trig identities, but it's more straightforward than the triple integral with square roots in it. Asking Mathematica to compute those two double integrals, I've set up the integral in Cartesian coordinates and the integral in spherical coordinates. And if you work these integrals out, you will get pi over 30 as your answer. Okay. So that's the setup of a problem in spherical coordinates. You just have to transform the density function, and don't forget your compensation term on your integral of rho squared sine phi, and then you need to describe the region in terms of the rho, theta, and phi variables. Okay. You could probably play around with the density function here, but you want to be really careful because let's see what happens here. You can get different densities in different slices, but even in spherical coordinates, these integrals can be quite challenging to do. So I think you can see here that in the x is equal to 0 slice, we've got a constant, but as you slice this function at 0.5 with this density function, you can see that there is some y variability in it. So this is why we have some actual color change, some actual different densities in this slice. And then if you try to find the mass of that region, same region, the only thing that changed was the density function, you still in both cases get the same integral, pi over 96. I'm not saying these integrals are easy to compute in spherical, but they are more straightforward than the ones in Cartesian coordinates. So I will leave you to try to evaluate this integral. Okay. And that ends this video.